Welcome back to this Cauchy linear situation again. So, we were discussing about the Cauchy linear equations, and then we are we have introduced what are called the characteristic curves. So, I have this system called dx by dt equal to a, dy by dt equal to b and dz. I call it that is star. Okay. So, basically you look at any point x naught, y naught, z naught, x naught, y naught, z naught in R3. So, you have a point here and then solve star. Okay. Solve star, that is an ODE, is an ODE system with the 3 components. Okay. And then you can uniquely solve. So, every point you will have a curve here. This is in R3, you have to understand that. So, you will have curves all along. So, these are called the characteristic curves if you want it, if you want to put it, characteristic curves. Okay. So, every point passing through, so the whole region R3 can in principle filled with that curves. So, what we are looking is that, so integral surface, so if we can form a surface, if we can form a surface S using these characteristic curves, then S will be an integral surface, then S will be an integral surface. That is what you are telling. The converse is also true. So, you have your region R3. In the region R3, you are looking for any point and solve that ODE to get a curve. So, vary that point. So, you will have a kind of, because curves are in some sense is a one dimensional object. So, you have some 2 dimensional class of, I do not want to call dimension, but you can see that kind of 2 parameter or whatever it is. You will have a set of curves filling the R3. From that I can form a surface using these characteristic curves, then that surface will become an integral surface, because these curves have the property its tangential directions are ABC. So, if you form a surface using only one family of characteristic curves, then it will, the only thing for a surface to be an integral surface, the only condition to be satisfied is that that tangent plane contains that tangential direction. That is exactly this thing. Only conversely, the converse is also true. Converse is also true in the sense, suppose you have an integral surface. Suppose S is an integral surface. What does that mean? You have a surface here. You take any point. Now, the point will be x naught, y naught, u of x naught, y naught. You have to see that, because it is formed an integral surface. You have your omega. Okay. Now, what I do is that I introduce an ODE, introduce dx by dt is equal to a of x t y t u of x t y t, because u is not to u now, because the surface is an integral surface. Earlier situation, the previous thing is that given a surface you are forming integral surface, when that surface becomes an integral surface from. So, the surface is formed from the integral curves. Here I am telling that the integral surface you start with it, you can decompose into integral curves, and dy by dt Now this is a complete system because the third component is known to you. Now you define the third part, d set t is equal to u of, this is you can determine xt, you can write zt is equal to u of xt by t. Then if you compute dz by dt, do this computation, this is a small exercise. If you compute this, you can see that this is nothing but c. Okay, you just do the computation, use the PDE, you get it. So in conclusion, what we have done is that for every point you can have an integral curve in R3. If you can form a surface using these integral curves, you get an integral surface, a surface which will be an integral surface. Conversely, if you given an integral surface, then I can decompose that surface into integral curves. Okay. Now with this information, we will go to initial value problem for Cauchy linear equation. So now let us have an initial. So the initial value problem is the same. The interpretation, the geometry behind the Cauchy linear equation and the complications arising due to the non-linearities are different. Okay. So what is your PDE? So let me find once more, call it, since I am introducing my Cauchy xy u ux bxy u uy minus c xy u equal to 0. This is your PDE. So you have your domain here in 2-dimensional domain. Okay, so this is not what I want to do. So you have your 2-dimensional domain here, omega, this is your x, this is your y, and then you are looking for a, and then you have an initial curve. So the initial curve gamma naught, you have to understand the data. So you have your gamma naught is given as the initial curve x naught of s, y naught of s, 0 less than or equal to s, less than or equal to 1. That initial curve, this is given, and u equal to u naught of s is also given. So what is the initial? So this is the complete data. PDE is given, your initial curve gamma naught is given, u is given, and find u in a neighborhood of gamma naught, satisfying PDE plus initial condition. Okay. So that is it. Okay, that is your initial value problem. Now how do you solve it? How did we solve it in the linear case? In the linear case, you are try to find the characteristic curve along the curve gamma naught, which was not possible. So what I am going to do it, lift this curve. So the method, okay, lift gamma naught to gamma naught bar by adjoining my initial conditions, initial value x naught of s, y naught of s, and add u naught of s here. So this will be a space curve. What did I do? Basically, you have this, you have your initial condition, you have x here, y here, you have your u here. So you have your domain here, and you have your gamma naught here, on gamma naught, I will get a space curve gamma naught bar, because I do not know how to find my characteristics here. So, what do I do here is precisely the problem is that for each point now I find, because now I know the how to find a space curve as an initial curve. So, each point here, so the any point here will be of the form x naught of s, y naught of s, u naught of s. Okay. Along that initial curve, so you solve your equation. So, you solve your 3-dimensional equation exactly that. So, what you do is that you fix x, fix s and solve for x t the curve, but that depend on s. So, you write s here, y t s, z t s, z is u, end of it, s satisfying such that dx by dt, dx by dt is equal to a of x t y t x t s everything x y z, okay, dy everything in t variable, okay, dy by dt equal to b of that, and dz by dt is equal to c of that, with the initial condition x at 0 s is equal to x naught of s, y at 0 s is equal to y naught of s, and z at 0 s is equal to z naught of s. You see, you solve this. So, you have a system of three unknowns x, y, z with initial condition. So, when you s you change it, you have a characteristic. As I said, the last 2 hours we are discussing that there is a question of inverse. Given a point, there will be a characteristic curve which passes through that. Yes, we need a condition. Now, it is time to state the theorem. Okay. And then I proof is just inverse function theorem. So, I will give the theorem here. Okay. Let a b c, so let me put conditions a b c be c1 functions of, b c1 means continuously differentiable, c1 functions of x y z, okay, in a domain R3, okay, in a domain R3. Okay. Let gamma naught bar be as above the initial curve given by the problem. Gamma naught is the initial value curve given by the problem, and gamma naught bar is the and x naught, y naught, z naught is the curve describing the initial value. Assume x naught, y naught, z naught is in C1 now, it is defined in one variable thing. And the important thing is about the assumption for the condition of to apply in assumption. This is called the transversality condition, transversality condition. Okay. What is the transversality condition? You look at the value at the initial curve. This is so x naught of s, y naught of s, z naught of s into dy naught, that is the tangents to the. So, you have to understand what this condition meaningful, minus b, again same argument dx naught s by dy naught of s, sorry, ds, this should be not equal to 0. I will tell you that you have the physical interpretation. I exactly tells you. So, this is your transversality condition. This is the additional condition. In addition to the smoothness of the theorem, you have to satisfy this additional condition. Then there exists a unique solution uxy defined in some neighborhood of gamma naught, which satisfies the PDE, and initial condition, and so that is the theorem. So, what is this transversality condition means? So, go to the next page. So, you have your initial curve, gamma naught, and then at this point you have your tangent, that is nothing but x naught dx naught by ds. I am using two different notations, that is all, y naught of s, and then AB is your curve direction. This is some A, B will give you a direction here, given by A of x naught of s, y naught of s, z naught of s. The condition tells that these two directions condition implies, the transversality condition implies these two directions are not are independent. Two directions are not parallel, right, independent. That is what it is. In other words, you are given in terms of the orthogonality. So, if you look at the back the condition, so dy naught minus dx naught will be the normal, okay, and that should not be orthogonal to that. So, you have that direction here. So, you this is given by x naught of s, y naught of s, okay, and this is AB is part of your characteristic direction. That means this gamma naught should not be a characteristic direction. It should not be it's at any point of time your gamma naught has to, it should not be a characteristic direction. It should not indicate the characteristic direction, because AB gives you the direction towards the characteristics, okay. So, the condition is precisely your gamma naught has to be a non characteristic, that is what. You will learn more and more about, as the course proceeds, you will learn more about your gamma naught. This is exactly what we have observed in some examples. If your initial curve happen to be a characteristic curve, the other characteristic curves will not come and intersect the characteristic to transport the values, and what we have done is a precise definition of that. So, let me give you a quick proof of it, because you almost done everything. So, it is a one line proof, it is an application of it is just an application of that. So, we have done almost all the job. So, you have your gamma naught bar. So, you have your gamma naught bar, and you know that every point you have a characteristic curve. So, this point is x naught of s, y naught of s, z naught of s, okay. And then what do you want? So, you have every point you can have characteristics, okay. Now, the issue is that you take a point here, you want to know does there exist a characteristic. So, you want to know, so the given, so you solve your ODE, system to get your solution of the ODE, which let me denote that solution by x. It depends on s, I told you, x, y t s and z t s. Okay. And this is a solution to s, right. Now what do you want? Starting with an xt, okay, you want to find a characteristic which meets your characteristic initial curve, lifted initial curve. That is what you want. In other words, what you are looking for, a characteristic curve described by the parameter t, and then sorry, here this is not a t because we used the t, this should be y. Okay. Given xy, you want, in other words, given xy in a neighborhood of gamma naught, wherever it is, neighborhood of gamma naught, solve for T s, solve for T s such that x is equal to x T s is equal to, this is what you want to solve it. You want to see that there is a characteristic y T s. This is possible by implicit function theorem or inverse function theorem, both are fine. Inverse function theorem, if the corresponding determinant is non-zero. So, dx by dt, okay, dx by ds, dy by dt, dy by ds not equal to 0. This condition of determinant of dx by dt, all that not equal to 0 is precisely your transversality. This is precisely the transversality condition. Transversality condition. Okay. So, by inverse function theorem, so by inverse function theorem, there exists t, that t will depend on now x and y. You can solve for t, s is equal to s x y uniquely locally, everything is local, uniquely, of course locally. Then you can compute your u x y as given x y, you have done this here, you got it, you have that, okay. Okay, u x y, you have your z of, you solve it, your z of what is the thing is a z, yes, capital Z of t of x y, you have solved z x t. So, you substitute and s x y. You can actually do a verification. One can do a verification that this is indeed a solution. Okay. I will not do that one, I will you can do that. You can compute your ux will be z corresponding to that, all that you can process, you can do that one and you can show that it is indeed a solution. So, that way using the, you see that immediately the effect of function inverse function theorem, using that you can actually solve in a, it is all local result. So, the theorem is local, but this method of solving using characteristic, quite often you can produce a bigger solution as a global solution. So, the theorem is local, but it is possible that while solving your differential equation you will get a global solution. So, with one example, maybe with one example I will example. Okay. So, last I think so let us consider a equation ux. I will not do all the calculations, but you can do the calculation. Uy equal to 1, what is the initial conditions? With the initial conditions, computations you can do it, I will tell you the method, and but try to work out more example. Initial conditions x equal to s, y equal to s. What is that curve? You should understand that curve. I am giving it in that format, x equal to s, y equal to s, and your u equal to s by 2, and I am solving 0 less than or equal to s. So, your values in diagonal is given. So, if you look at it here, it is given along this diagonal, okay, right. So, x equal to s, y equal to s, and your values are given along the diagonal. The values of u are given along the diagonal. Okay, so let us do. So, what is your a? A is equal to u, your b equal to 1, and c is also equal to 1, right. That is very clear. So, first verify transversality condition. What is your transversality condition? A along the curve. So, your curve is this one. So, A along the curve, A is nothing but u, and u is s by 2. So, A into y naught prime s, everything is in s, okay, minus b x naught prime of s. What is this? A is s u, right, and along the curve it is s by 2, that is s by 2. And what is y naught of s? This is x naught of along the curve. This is your x naught. So, let me write that also. Your x naught of s equal to s, y naught of s is equal to s, and your u naught of s, something you can also use it as z naught of s if you want, equal to s by 2. So, this is your initial condition. So, this is s by 2, your y naught prime is equal to 1 minus b is equal to 1. So, that is 1, and x naught prime is also equal to 1. So, and 0 less than s less than 1. So, this is actually it can never be 1, this can never be 1. So, this is not equal to 0. So, the transversality condition is satisfied. Now, try to solve it. You what do you want to solve it? Now, solve dx by dt equal to d is equal to u, right, dy by dt is equal to 1, and du by dt or dz by dt is equal to 1. Okay. With this initial condition x naught of s is equal to 1. So, what you will do? You can solve these two equations directly, right. That is easy to solve it. What do you get it? If you solve it, your yts will become, it is 1 integrate. So, you get a t yts will become, if you integrate this one, it will become t plus a constant will come, but y at 0 is equal to y naught of s. So, that is equal to s. So, you will get s here, and then you will get uts is equal to, or zts is equal to, again here you will get t plus, then the constant is s by 2. So, you get s by 2. So, you have to solve this equation now. because you determine. So, let us do it. So, you have your dxt by dt t plus s by 2, that implies xts is equal to ts integrate, that will give you t square by 2, this will give you st by 2, you see. So, you have everything in terms of xts. So, there is an invertibility. So, you have an xts. So, let me write once more, xts is equal to t square by 2. So, you can do some work, st by 2, and yts is equal to t plus s, and then zts is equal to, you have to invert now, or uts equal to, uts is equal to uts is equal to t plus s, t plus s by 2 maybe, right, yeah, t plus s by 2. So, you want to invert this, which one is x equal to xts, you have to invert, y equal to yts, you have to invert. So, if you invert, that means you have to write down your x and t and s in terms of thing. I do not do the calculation, but I will write write down, you get t is equal to, solve this equation exercise. This is a simple exercise to solve it. You get your t is equal to y minus x by 1 minus y by 2, and you get your s is equal to x minus y square by 2 by 1 minus y by 2. Substitute, that implies, so you substitute in the values of uts here, you substitute here, and then that will give you your uxy. Try to work out more and more problems. Okay. 2 into y minus x, please do this computation, small computation, it is not a difficult computation, x minus y square by 2 by 2 minus y. Okay. So, that completes what I want to discuss about the Cauchy linear equations. My plan was even to complete the nonlinear case in this half an 2 hours, but I could not make it. So, maybe we will take another half an hour. So, the 2 hour plan is maybe another half an hour. We will do the general nonlinear equations, and then that geometry is little more complicated, since we are already done this one. Try to get, so before going understanding step by step, if you are before going to the Cauchy linear case, try to get understand the linear case properly, try to solve few problems from the linear case. After understanding the linear case, the situation, you go to nonlinear case. Understand that nonlinear case geometry behind it, you immediately see the different from the plane you have to go to space. But then when you go to nonlinear case, now you can't go further up, because there is only 2 variable and unknown. So, 3 space, you have to still remaining in, you have to still remain in the R3 space, but the geometry is little more complicated. You have to understand the thing. There are concepts like Monge cone and characteristic strips and all that. So, we will take up that in the next quickly in the next half an hour, and try to tell you the geometry. Once these 2 dimension things are completed, we will go to n dimension complete. So, thank you, we will complete it.